Hello statistics student, this video is for chapter 10.3 hypothesis test for two proportions. Now these two proportions are from two different populations. So we are not talking about, okay, in one population I have I'm checking who answered yes, who answered no, how many percentage answer yes, how many percent answer no. No, that's not what we're doing. We are comparing two different populations. Say, for example, male and female. That's what you're doing in your project. You have two different sets of people, but you are comparing a same proportion parameters. For example, for the male and female, what is the percentage that are full-time in the two population, but we're talking about same thing, full time, okay, same category. Another example would be we can look at two different population. This is all the population of M&M candies, right? And this is the Skittle candies. It's Halloween time, so we have candies. So we're comparing a same population, a proportion, two different population, but two proportion. They all start with P. So this is red candies. So you want to see what is the percentage of red candies here and what's the percentage of red candies. So they're the same thing. You're not comparing red candies here with blue candies here. They have to be the same category of proportion. So you're trying to see the percentage in this population, M&M and Skittles, for example. So what are the claims about? We're not talking about claim values anymore, like in chapter 9. We're talking about if the population parameter are different, if the percentage of red candies in both of these are the same, different, or one is higher than the other. Do you think the Skittle candies has more red? So maybe you can claim that there's higher percentage of red candies in Skittles than M&M. You are not talking about claiming, oh, this is 10% or 20%. You're just comparing them. You're comparing the two percentage if they are same, if they're different, or one is higher or one is lower. And if there is a difference, you can also use the sample. Of course, you can't count all the candies out there. So you use this sample, get a sample from the first one, right? We call it sample 1, and get a sample from the second one. We call it sample 2, not because it's the second sample, it's really because it's from the second population. So you will look at these two samples to estimate the difference. So what is the percentage difference? You don't care about what they actually are, but you want to see how much higher is Skittles M&M's red percentage than the red candies percentage in M&M. So this particular objective, these are the objectives in chapter 10, and we are talking about 10.3, which is proportions. We'll get back to 10.1 and probably not do 10.2 because it's not really useful in daily life, and 10.4 after this lecture. So there's some terms that we want to introduce before we go into the detail. The first is significant difference. When we say different, samples are always different, right? Even if I have the same population, this is a population I'm looking at. If I get one sample here, and I get another sample, and I like in M&M, you get a handful from a bag of M&M, so the percentage of red in both of them are different, right? So there will be different, but the difference is not significant, meaning they are just difference in that is within the boundary of sampling error. You know how different they are because all percentage p hat are normally distributed, so they could vary and they would have a range that they vary. So taking into consideration of sampling error, even if we see two samples had different proportion, they actually should be the same. So, and then the other terms that we want to look at, this will be discussed in more details in 10.1 and 10.4. In particular, 10.4 is samples called independent samples versus dependent samples. Samples are independent if the value are not naturally paired. So, for example, I have a sample from an M&M candies bag, and then I have another sample from a Skittles candy bag. Each individual pieces are not related to each other. They're not paired up. Okay. Versus sometimes we say, okay, I'm going to interview male and female, but the male is and female are from a couples. One is the wife, one is the husband. So although we're talking about two populations, one male, female, but they pair up. So those are called dependent samples. And we'll talk more about those in 10.4. So actually, how are we going to compare sample from two different populations? And how do we inference? How do we make conclusion about the proportions? How do we know that they are the same, difference, or one is higher than the other? So the procedure that we're going to talk about will help us to test a claim as well as estimate confidence intervals of the difference of P1 minus P2. That means proportion 1 minus proportion 2's difference. Now, when we subtract two numbers, there may be negative. It could be a negative number if P1 is lower, right? So when we do confidence intervals in this section, the lower limit and upper limit could be positive, could be negative. Okay, so how do we do that? So this is the notation and also theory. So if we took one sample from population 1, the sample size is N1. The one that we are counting is X1. Like for example, we are counting red candies, then X1 is the number of red candies. The second sample is from the second population, maybe Skittles. So we have another sample size and it's X2. So these are sample proportion from two populations. Sometimes we calculate them, sometimes we just use them. If we don't know X1, N1, sometimes we would actually have to do N1 times P1 hat, and X2 is N2 times P2 hat. And when we calculate this, make sure you round to whole numbers, because when we're talking about proportions, these X and N's are whole numbers. So this need to be round. So I'm going to do one example where I have to do rounding to whole number if I don't know X1 and X2. Just remember you need to round them to whole numbers. Now, we are trying to estimate the difference of P1 minus P2. So when you get the two samples, you immediately see the difference. So they most likely are not the same. So what happened is initially in chapter 8, when we do confidence interval, we know P hat is always normally distributed, right? P1 hat is normally distributed. So if you collect a lot of P1 hat, they are normally distributed. P2 hat is also normally distributed, and they have a standard deviation is equal to square root of P1 hat, Q1 hat, or this is actually the estimate over N1. This is P2 hat, Q2 hat over N2. You still remember this? This is so if I get both of them and I subtract them, what about P1 hat minus P2 hat? This number is going to change, right? So because P1 hat is any number in between, P2 hat is any number here in between. When you subtract two numbers, it turns out that the difference between two normally distributed random variable is also normal. And in when we do hypothesis tests for comparing two P1 and P2, we always think that they are zero. The null hypothesis is always when you subtract them, they are zero. That means they are no difference. Null hypothesis say no difference. Temporarily assume that there is no difference. So then how does P1 hat, P2 hat spread out? So they spread out by all this tick mark, right? So the standard deviation that we have is actually calculated by P bar Q bar over N1 plus P bar Q bar over N2. So this is the variance of the first one, the first sample, and this is the variance of the second sample. What is the P bar? We only have P1 hat and P2 hat. P bar is because we are assuming in the null hypothesis that there is no difference between P1 and P2. So we just combine them. We thought that they are actually the same. So we assume that they're actually one big sample but split into two halves. So the pooled sample will allow us to pool the variance. So this is the way we calculate this as a statistical term called variance, pooling of variance. So if you pool the variance, the error would be lower. So P bar would be x1 plus x2 over n1 plus n2. So this part is theory. So you don't have to calculate them, but you need to know that when you calculate, when you use two samples of proportions to do a hypothesis test, the way we do is this SD, each one of these SD is P1, P bar, Q bar over N1 plus P bar, Q bar over N2 because we are pooling the variance. The reason why we can pool the variance is we assume that they are actually the same proportion. So if you have the same proportion pooling together, you just have two samples that you're comparing. Okay. So, and they are normally distributed. So now, if they are normally distributed, we can look at the sample and figure out if P1 minus P2, is it very unusual based on the fact that they are the same. So these are the steps. Okay. So the previous one is about the procedures, about the theory. Now is about the step. The steps are very similar to when we do a hypothesis test. So first you write down your population. The only difference is you have two samples, so you have to identify which one is from which. Okay, so first is to record population 1 and 2, write down n1 x1 and 2 x2. And the requirement for them to be normally distributed is the number of success and failures are at least 5. The second part, very similar to hypothesis test, is to record the claim in symbolic form. Write P1 is greater than, less than, equal to, or not equal to. You can have anything for the claim. And then write X0. X0 is always P1 equal to P2. And the alternative hypothesis would be either less than, greater than, or not equal to P2 in symbolic form, so that one of them must be the claim, just like before. And then either the X0 or the alternative hypothesis is exactly the claim. And if X0 is the claim, when we do the conclusion, we use reject, remember? And if X0, X alternative is the claim, when we do conclusion, we use support. Then the third step is just write down your significant level. Is it a left tail, right tail test for the alternative hypothesis? And for proportion, the distribution is Z normal. Then the important part, the next part is to calculate test statistics and p-value. So the procedure that we use is StatDis. So when we do an example, I'll show you. So basically StatDis, hypothesis test, proportion, two sample because we're comparing two. Your output should have a test statistics as well as a p-value. Test statistics describe how your P1 minus P2 is differ from 0. How many tick mark it is different from 0. The p-value is indicating how likely you are to get that big difference or small difference if P1, P2 equal to P2 is true. Meaning, so all these calculations are basing on the null hypothesis being true. Then the confidence interval would be given. Now, unlike the old hypothesis test, we will actually use the confidence interval here. Okay, so the conclusion is the most important part. If p-value is less than alpha, the significant level, you have a rare sample, so you would reject X0. And if the p-value is greater than alpha, you don't have a rare sample, you say, oh, it is the same old. It is predicted by X0, so you say fail to reject X0. Okay, and then you can immediately say that there is no difference. They are actually predicted by X0. Now, when you do the hypothesis test, at the end, you also will have a confidence interval. Okay, so write the claim first. The claim would be there is sufficient evidence if there is if the sample is significant and there is no significant, and if you do reject, if your claim is X0 and you support if claim is not 0.